Good afternoon, everyone. Thank you for still being here. I'm conscious of getting late in the day. Yeah, I'm Paul. I'm from GNS, and I'm going to talk a little bit about how we currently assess volcanic ash hazard, well, assess and communicate that, and a little bit about what we want to do in the future going forward. Does that? Yeah, that works. So I'm very quickly going to talk about what volcanoes we have here in New Zealand, and then move on to what we at GNS do, and then talk a little bit about the present work the current state of affairs, and then what we're going to do in the future. So we have lots of volcanoes here in New Zealand. We have, most of them are concentrated, do the mask because you look at both screens, along what we call the topo volcanic zone, which runs from Whakaari White Island in the north down to Ruapehu in the south. But we also have Taranaki, Auckland and Northland further over to the west. So yeah, overall, we consider that there are 12 potentially active volcanoes in New Zealand for which we set alert levels and which we monitor. So GNS, what we do, we monitor all of New Zealand's geohazards through what we call the GeoNet program. Volcano is one of those hazards. We monitor these volcanoes using a mixture of instruments on the ground, sampling gas and fluids from these volcanoes, and also through collaboration with our colleagues at Met Service, satellite observations. Within the GeoNet program, we have the Volcano Monitoring Group, who are responsible for these day-to-day monitoring operations. However, supporting that, we have the 24/7 National Geohazards Monitoring Centre, an on-call volcano duty officer, who right now is me. So if my phone starts blaring, I might disappear, but unlikely. And a volcano science advisor, who is also on call. Based on the monitoring we do, we also issue scientific advice to government, emergency management, key partners, and the public. How do we issue that advice based on the monitoring? So we have 4 core products: volcanic alert levels, aviation color codes, volcano activity bulletins, and volcano observatory notices to aviation, VONAs. But we also have ash fall forecasts, which I'm going to talk a little bit about later on in the presentation. So volcanic alert levels, like our main core product. This is our system by which we basically summarize the state of a volcano at any given time. So we have six levels going from 0 to 5. Level 0 means the volcano isn't doing anything. It's basically acting just like as a mountain. And levels 1 and 2 correspond to what we call unrest. So there is activity. This may, for example, at Ruapehu be the fact that the lake at the top of Ruapehu is kept hot. But the volcano is not erupting. And then levels 3 to 5 tell us about, say the volcano is erupting, from a small eruption up to a big eruption. And I have some examples in these photos of what those types of eruptions could look like. Currently, only 2 of our volcanoes are at non-zero levels, and neither of them are erupting. We set the alert level each week. Everyone in our volcano monitoring group votes for each volcano every week. However, if there is more of a time pressure because activity has started quite quickly, the volcano duty officer and volcano science advisor can set it together. Or if there is an immediate risk to life safety, the volcano duty officer can make the decision by themselves. If you want to know our current alert levels at any time, you can either go to our GeoNet website or download the GeoNet app. You can use those QR codes there. They'll appear again later if you missed them just now. We also issue, I realize these colors are awful, aviation color codes. So for each volcano, it can have an aviation color code from green through yellow to orange to red. And this is a specific product which we issue for the aviation industry. Currently, Whakaari White Island is yellow, and all of our other volcanoes are green. Yeah, not much more to say on that one. VABs, our activity bulletins. So these are New Zealand's official source of information. And we will issue these if we change an alert level or an aviation color code, or just to provide a general update. Sometimes we haven't had to issue one for about 3 months. So if a volcano is at alert level 1, we like to issue another one just to keep people informed. Sometimes these will also contain ash forecasts if we have to issue them. Again, you can find all of these on our website or go to the GNet app if you want to. And our other final core product is what we call Vivona. This is an internationally defined template, which is for disseminating critical and operationally relevant information about volcanic activity for aviation users. And according to ICAO guidelines, these should be issued when we change the color code, or within a color code when an ash producing event or a significant change occurs, or that last criteria when you have episodes of resuspended ash. So this is ash which has erupted previously and is now being lifted up into the atmosphere by the wind. That's not something which happens much in New Zealand, or not something we'd necessarily expect to happen much in New Zealand unless a major eruption was to happen and dump a load of ash on the ground. But does happen around the world in dry, arid areas. For example, I think a photo from the Cordon-Cauge eruption was shown earlier today. That eruption dumped a lot of ash across Argentina, and for many years afterwards, that was being lifted up into the air, posing a hazard. So the crux of what I want to talk about today is about how we actually do hazard assessment for volcanic ash. So first of all, what is volcanic ash? It is literally the fragments of rock formed from the explosion of the magma. It can be very abrasive, hard, sharp, angular, and it can also be electrically conductive or corrosive due to the chemicals which coat its surface. And it's these properties, the corrosiveness, the abrasiveness, and the conductivity, that really mean that it is very hazardous. Where does the ash go? When an eruption happens, first of all, it's initially lifted upwards due to the buoyancy of the volcanic plume. You can see that very nicely in this photo from Ruapehu. And then it disperses with the wind. So you can see in the satellite image of the eruption from Tongariro on the 6th of August 2012, there was a wind headed and it took it off towards the east coast. Volcanic ash can be impactful both on the ground and in the air. And the type and scale of that impact really depends on the amount of ash which you get. So forecasts of ash are really useful for decision makers, which could include emergency management, infrastructure managers, and I've sort of highlighted here, airport operators, but also anyone who's responsible for buildings or, power supplies, for example, because those are, I imagine, people might be interested today. And the extent of impacts you expect, closer to the volcano, you will have more ash fall on the ground or be in the atmosphere, and so your impacts are potentially much greater. But ash is, can have impacts far away as well in what we call the distal zone. In order for these forecasts to be effective, they need to be rapid, they need to be reliable, so they need to be ideally both accurate and we know the uncertainty on them, and they need to be dynamic in that we can actually update them as more information comes in or as the properties of the eruption change. Currently in New Zealand, there are two sort of types of ash forecasting that happen. What I'm not going to talk about, but what Nicole has already covered, is what Met Service do through the Volcanic Ash Advisory Centre, who talk about forecasting the concentration of ash in the atmosphere and issuing products such as the volcanic ash graphic I've put up here. And GNS, through the GNet program, we will issue ash fall forecasts. So this will tell you about the amount of ash accumulation on the ground. Obviously, if you're an airport operator, you probably care about that quite a lot, or if you're responsible for any of the supporting infrastructure around that. We sort of have two types of ashfall hazard map. The first type are what we call background hazard maps, and these are useful for planning and readiness activities. And there are two types. We have scenario-based maps. So these can be a representative example of eruptions. For example, here we have one for Taranaki volcano, and it shows an example of a moderate eruption, and it's based on an event in the past. And this can be used as an indicative example of what you might expect. The second type is probability-based. And so to do this, we will simulate the ashfall from many different eruptions. And we will base that on data from historic eruption frequency and historic eruption properties, and also typical temporal probability distributions of wind fields. And you can also do this including multiple volcanoes. So this example here, the contours show you the ash thickness expected with a 10% probability over the next 50 years based on eruptions from a bunch of volcanoes in that topo volcanic zone from Ruapehu up to Okataina and Taranaki. The second type of ashfall hazard map we have is what we call a response map. And this is what we would issue if an eruption has happened or we consider that an eruption is imminent or likely. In this case, we'll be simulating a specific event, which ideally is representative of the actual eruption which is occurring. And ideally, we can revise and update this map as and when more information becomes available. To generate this, you would use the most up-to-date weather forecast available. But it's always important to acknowledge that, like all forecasts, there are sources of uncertainty. Similar to what Nicole mentioned, you have the eruption source parameters, which we need as inputs for these models. So that's the height of the plume, the volume of ash coming out, the time the eruption starts, and also the ash size distribution, and then also uncertainties in the weather forecast as well. So how do we do this at the minute? Through partnership with Met Service, our forecasts are produced using a model called HighSplit. This is created and maintained by NOAA in the US. It's widely used globally to model the trajectory and dispersion of a wide range of sort of materials in the atmosphere, including volcanic ash. What we do, so all the time, every 6 hours, we simulate different scenarios for each volcano, a combination of small, medium, large eruptions and low and high plume heights. So for example, in this image here, this is what would be expected for a 12-kilometer high volcanic plume with an eruption volume of 0.1 cubic kilometers last May the 7th. And the outputs from this model, we can produce the forecasts and forecasts, we can produce thickness and timing forecasts. And these outputs are automatically displayed on a dashboard accessible by our volcano duty officers. And just as a contrast for a different scenario, this is if you had a low, small eruption from the same volcano at the same time. You can see you get a lot less ash and it goes in a quite different direction. So in the event of an eruption, our duty officer will, once they've confirmed an eruption occurred, we will issue an initial volcano activity bulletin, just notifying that an eruption has occurred. And then amongst a bunch of other stuff, we will go to our dashboard, select the scenario we think is most like the current eruption. We'll perform a bit of manual quality control because sometimes the models don't produce realistic results. But if it does, we'll take the graphics and insert them into an ashfall forecast template, which looks like this on the right-hand side. And we'll send that out as a volcano activity bulletin. Page 1 of the forecast will be this map, along with some technical details on the model and the scenario used. Page 2, we have some plots which show the timing of ashfall expected in different locations. So for example, that top right plot shows the time at which you expect to receive ash in New Plymouth. We also include a qualitative summary, so text-based, and then some general useful information on ash hazard. And then on the final page, we describe some of the impacts, some general advice and actions, and some links to further information. So, in terms of what's happening in the future, what do we want to do to improve this? We have our current challenges we're trying to address. One of the challenges is about how do we actually refine these forecasts. At the moment, the forecasts we generate and the forecasts we disseminate are predefined scenarios, which are designed to be issued in that immediate response when we have very little information on the eruption source parameters. But we want to be able to update those forecasts by getting data on the plume height, the volume of the eruption, and the time of the eruption. And we don't currently have an automated provision either for obtaining that data or generating the forecasts. Secondly, our current models are deterministic. So what that means is we simulate one scenario and we just input parameters and get an output. So they don't account for any uncertainty in those inputs. So what we are currently working on is developing probabilistic forecasts. And to do that, you can determine a probability distribution of your inputs. So for example, in this graph here, this is a plot of volcanic plume height. And the line shows the probability. So it says the most likely plume height is about 10 kilometers, but there's a 95% chance it's within this pink region. So we can sample that, we can develop these probability distributions for all of our inputs, sample them, and run a large number of simulations, and then we can produce a probabilistic measure of ash thickness. And so here's an example here of a probabilistic ashfall map, and the color tells you the probability that you get more than 0.1 millimeter of ash at a given location. Essentially, though, to be able to do that, you need to have an idea of what these probability distributions are of your inputs. So to address both of these challenges, what we really need is a better characterization of our source input parameters. So to try and address this, we've recently started a new project where we're trying to really develop a suite of tools where we can use various data sets. So this is, for example, weather radar, satellite, acoustic sensors around the volcano, seismometers, our webcams, and also GPS stations. Use these different data sets to rapidly estimate our eruption source parameters through the use by combining the data with various numerical models. And you can see different data sets, we can get different parameters. Combine those different estimates into what we call these probability density functions for the source parameters, and then input them into our forecast models to produce the probabilistic forecasts. So as part of this, we will be testing these methods, these individual methods against historical eruptions. So testing these individual methods here, as well as the combination. And we're also looking to apply these tools both here in New Zealand and across the broader Southwest Pacific. Over the next 3 years, we really are hoping to engage with multiple partners to really ensure that actually not just do our tools work scientifically, but actually the tools we create are actually usable and generate output, which is actually useful for our partners, because otherwise there's not really much point to doing it. So I think that's me done. I just got a couple of last slides. On the GNS website, we have links to various resources which provide information on volcanic ash hazard for specific sectors. If you would like to access any of those, you can access them through this QR code here. And just to wrap up, we produce a range of volcanic advice products which can be accessed through the GNet website or app. All of New Zealand's active volcanoes can produce ash, and ashfall can cause a wide variety of impacts. And in a response, we will issue ashfall forecasts as a VAB, which will include maps and a text-based summary. But we're really looking to go beyond that and try and produce more quantitative forecasts available in a more usable format. And that is me. Thank you very much.